Okay, let's get started. I will come back to these problems in a few moments. First, let's start out with some course announcements. First, Vincent's office hours will be moved to 10:30 a.m. on Thursdays. We will be posting links for office hours. They will take place in, I think, a different Zoom room than this one. Please, if you haven't already, join the Slack workspace for this class. Everyone should have already gotten an invitation. If you have not, please email me if you are in the class either for credit or as an auditor. Finally, problem set 1 is out. It's on my courses. It's also in the Slack. And it will be due on Friday, September 18th at 11:59 p.m. That's Montreal time. Please submit your solutions through the My Courses page. Or if you don't have access to that, which is the case for some auditors, you can email them to me and Vincent. But please do My Courses if you have access to that. Finally, I wanted to say again what we've been discussing in Slack. Given that today and tomorrow is that many academics are participating in the scholars' strike in protest of systemic violence against Black and Indigenous people, both in Canada and the US. Feel free not to attend this class. Attendance today is not mandatory. If you are participating in the strike, please do attend if you are not participating in the strike. Thank you everyone for voting. We decided to have class today because a strong majority of the students in the class wanted there still to be the class and to stay on schedule. But I do encourage you, even if you aren't participating in the strike, to check out the materials that have been produced and the program that has been developed by the strike organizers. There's a URL in the Slack about that. I believe that material will be recorded, so you can go and listen to that at your leisure, even if you're not watching it live today. Okay, are there any questions about any of that or about the class in general? Okay, feel free to ask questions in the chat at any point. Let's go on to that first problem, which I put as a teaser at the start of class. Prove the formula for triangular numbers. So the triangular numbers are just the sums of 1 up through n, as n varies. And there is this nice formula, n times n plus 1 over 2, which some of you may have seen before. There are different ways to prove this. There are geometric ways, but a way that has already been suggested in the chat, maybe can let some people discuss it a bit more. Any thoughts here? It is a bit spoiled by the fact that today's class is about induction. The idea is to use the principle of mathematical induction, which we will define in a moment. But the idea is, what if we knew that this was true for, say, 10? Then, would it be true for 11? If you add 11 to the left-hand side up here, you could also add 11 to the right-hand side. And if it were true for 10, this would be the case for 11. Let's see if we can rearrange the right-hand side there. And look, we can express this as 12 times 11 over 2, which is just the formula, what the formula would be if we'd done this with 11 instead of 10. Now, some people are posting in the chat these very nice geometric ways of thinking about it. I'll let you look at that at your leisure, or go online. You can find some nice geometric ways of proving the formula for the triangular numbers. Now, how do we make this into a formal argument? This idea of what if we knew it was true for 10, then we add 11, show it's true for 11. That doesn't prove it works for 12 and 13 and 14 and so on. It doesn't also prove it works for 1, 2, 3, 4, 5, 6, 7, 8, 9. And we also need to prove it works for 10. So there are a lot of different numbers. How do we prove for all of them? We can't do this an infinite number of times. So the general idea is, suppose we know that the statement is true for n equals k. And in this case, that's the statement that we're trying to prove. Suppose we add k plus 1 to both sides. Then we can rearrange this stuff on the right-hand side. If we add k plus 1 to both sides here, we can see that that means that we have the sum of the numbers 1 through k plus 1 equal to the sum of the numbers through 1 through k plus that new one that we added. And rearranging all of this gives us this nice formula, which is the k plus 2 times k plus 1 over 2, which is exactly what this formula would be if we used k plus 1 instead of k. So what we're showing is that if the statement is true for any k, then it's going to be true for k plus 1. Does this mean that we are done? Is this a complete proof of this statement? We can go from k to k plus 1 to k plus 2 and so on.
We need to show the base case, I think.
Yes, there is a thing called a base case, which is basically an n that starts everything off. Is this true for n equals 1? It's pretty simple to show that this works for n equals 1. Generally, base cases are very simple. Occasionally, you will run into a situation where the base case is actually really hard. But in this case, it's very simple. 1 is just 1 times 2 over 2. The formula works for n equals 1. So how does this work? Well, in general, suppose we need to prove something for all n is greater than or equal to 1. We prove it for n equals 1. That's the base case. We show that if it works for n equals k, then it works for n equals k plus 1. This is called the inductive step. And that means that n equals 1 implies n equals 2, which in turn implies n equals 3, n equals 4, and so on. This is a very general framework for induction. This is basically what we did in that last problem. We're going to see some different settings where it shows up throughout class. Some overall themes about when induction can be useful. Formulas for sequences of numbers, or summations of numbers. Proving what happens in a recursive algorithm if you're doing a thing in steps, and the steps sort of apply recursively. Or in general, when something can be reduced to a smaller problem. That's basically what we're doing here. And sometimes this is thought of in algorithms as a sort of divide and conquer approach. And induction is just really, really powerful in all of these ways. You'll often find that induction is the clean way to write a proof, which could be expressed in a much more messy way. So if you feel like you're ever having to say, well, from this situation, I can reduce it to this, and from this, I can reduce it to this, and from this, I can reduce it to this, and so on. There is a much cleaner way to do it, which is to prove it using induction. And we'll see in a moment what writing an induction proof actually means. Should the induction hypothesis be explicitly stated? Yes. So that what we saw right now is not a formal proof. That was just how you might think about the proof. So now we'll see a formal proof of the same thing. Also, I realize I didn't answer a question from earlier, which is about the LaTeX write-ups for problem set 1. There is a LaTeX template available both on my courses and on the Slack. I'm sorry, it wasn't immediately available, but now it should be available to everyone. So please, if you're using LaTeX, I encourage you to use the LaTeX template. Okay, so here's a formal proof of what we just showed sort of intuitively and informally. It's a good idea to say you're going to prove the result by induction. We will prove the result by induction. First, you can show the base case. Some people do the base case last. You can do it either way. First, we observe that the base case of n equals 1 holds, and then just show the base case. Here, it's really simple. Now, this is the inductive hypothesis. Suppose towards induction that the claim holds for n equals k. And then just stating what that claim is. And then here is the sort of inductive step. adding k plus 1 to both sides, we obtain this, and then rearranging this other side, we get this nice formula. Showing the claim holds for n equals k plus 1. This completes the induction. Always good to say, we're done with the proof. This completes the induction. Since we have our base case, since we have our inductive step, always make sure you include the base case. Then we've finished an induction proof. Questions about this? Or questions in general? Do we just assume that the induction is true like an axiom, or is this principle derived from something else like the Peano system of axioms? But for the purposes of this class, we will just be assuming that induction works. And for natural numbers, induction just works. There are like transfinite induction things, and you don't have to worry about induction on infinite sets. But for this kind of induction is just true. There isn't an axiom that you need in addition to the normal kinds of math. How to understand that induction is not the best solution? Oh, well, yeah, there are paradoxes which are supposedly, increasing something that's already infinite, like Hilbert's hotel and stuff. We'll get to countability actually in the next lecture, so maybe that's the better setting for discussing that. Yeah, so there was a question about for applying induction in integers is the suggested way to show for the base case and then prove for n plus 1 given n, and then proving for n minus 1 given n. Oh, if you were trying to prove for all of the integers, e.g. for negative numbers as well as positive numbers, would you start at 0 and would you go sort of both ways? That actually shows up relatively infrequently. But yes, you could do that if you wanted to. Normally, I find that induction is something which is being done just for the positive numbers, and that's not necessarily because you are actually proving a statement about the positive numbers. It's just because you're sort of counting. You start out with this base case, and then you go 1, and then you go 2, and these two things, 1, 2, 3, so on, could be like steps in your algorithm. So it's not necessarily really positive integers always. We'll see that in a bit. But yeah, you could absolutely do that, as Devon was saying. Okay. The harder version, which I mentioned, let's just quickly see a flavor of what that would look like. So this is sort of the, if you liked the triangular numbers, we're like, oh man, that's so easy. Well, here, this formula is somewhat useful sometimes, and it's just the squares of the first n integers and positive integers, I should say, and that also has a closed form formula. There are also formulas for like the sum of cubes and so on, and they get progressively thornier, and you can prove them all by induction. In this particular case, this is just an outline of a proof. I'm not going to go into a formal proof. The base case is really simple. Just taking 1, this is like 1 times 2 times 3 over 6, which is indeed equal to 1 squared. And then this is an induction, so we assume that it works for n equals k. This is what it would look like for n equals k. I've just plugged in k in place of n. And then how do we get from k to k plus 1? Well, we just add k plus 1 squared on this side and add it on the other side. And if we do some algebra, we can show that, in fact, this does simplify to what it would need to be for the formula to hold for n equals k plus 1. And I'm not going to go through that algebra because it's boring. But that is how you would go about proving something like this, if you want, by induction. And again, there are other ways to prove this. Let's take a look at another problem. I'll let you think about this for a moment, but I'll read it out loud. You've probably, many of you seen the Fibonacci numbers. Sometimes they start at 0, sometimes they start at 1. I'm going to start them at 0 for convenience. They are defined by starting at 0, 1, and having each following one being the sum of the previous 2. Prove that they have this nice closed form solution. This is called Binay's formula. Prove that the nth Fibonacci number is 1 over the square root of 5 times the difference between the nth powers of phi and phi bar, where phi is the golden ratio and phi bar is the conjugate of the golden ratio in some sense. I'll let you think about that for a moment. This is one of the reasons why people like the golden ratio, but it's not the only reason. Okay. What makes us think of induction here? Why is this a good thing for induction? Yeah, I mean, it's like there's this nice linear recurrence, it's recursive formula, that's a sequence. It feels like it's getting more and more complicated, but the start is sort of easy. Yeah. So it looks good for induction. So what would that mean? Like, induction means that let's assume that fk is given by the formula for some k. What do we need in addition to fk to prove this using induction? This is a different form of induction. It's basically the same. It's just, it's not exactly what we were looking at before, which was assume it works for k, go to k plus 1. Yeah, so people are saying something about previous two terms. So yeah, we also need the previous term before fk. And that's because if you look at this formula up here, if we're going to show something about fn, we're going to need something about fn minus 1 and fn minus 2. So let's assume a couple of things. Assume fk minus 1 has this formula. And we're also going to assume that fk has the formula. Now, how do we use that? We know from the formula for the Fibonacci numbers, and I deliberately have not gone to the base case here, but I know people are posting about the base case. We know that there's this formula for the Fibonacci numbers. So if we've already assumed that, the formula holds true for fk and fk minus 1, well, this is what we have for fk plus 1. So we would like to show that this fk plus 1, which is this thorny thing on the right-hand side, can actually be rewritten as this formula. So we'd like to show this. This would prove the inductive step. Any ideas as to how we can prove this? Besides, simply bashing out everything with a ton of nasty algebra. We could make a substitution. What's the simple thing that we can do? Whenever we have something that's super thorny, see if we can, let's just rewrite the terms. At the very least, we can just multiply out by square root of 5, and we can rearrange a bit. At least this is equivalent to the thing up there. If we can show this, then we can show this. So we've put all the phi's on one side. We've put all the phi bars on the other side. Okay, cool. Anything interesting we can use here? And this is using a fact which is not, which I'm not assuming that you know, but it's something which is super useful if you ever have to work with the golden ratio. If you have not seen this, it is not a problem. I will tell you in a moment. Basically, there is a fact which is why the golden ratio shows up everywhere in math. I'll just tell you this fact. Phi and phi bar are the solutions to this equation. And you can show that they're the solutions to this equation, x squared minus x minus 1 equals 0, just by using the quadratic formula. That means that you have, they are the solutions, so you have these equations. This is the key property of the golden ratio. That's why it is interesting. That's why it shows up in pentagons. It's why it shows up in the Fibonacci numbers. It's why it shows up in other contexts. So what can we do, given that we know that this fact? How can we use this fact to prove the thing that we want to prove? Post in the comments. Yeah, so we can divide by stuff. In particular, we have to be careful because we can't just divide this equation because this is something we're trying to prove, right? So we need to get to this equation from things that we already know. Now we know that this is equal to 0. So if we multiply these equations, this one we can multiply by pi to the k minus 1. What happens? Pi to the, we get different terms. So pi to the k minus 1 times 1 is pi to the k minus 1. Pi to the k minus 1 times phi to the k minus 1 times 1 is phi to the k minus 1. Phi to the k minus 1 times phi is phi to the k. Phi to the k minus 1 times phi squared is phi to the k plus 1. And likewise over here, we can multiply this and get this. And so that means that both this left-hand side and the right-hand side here are equal to 0. So not just, we don't have just that this equation is true, but actually both sides are equal to 0. There was a question about the variables being in vector format or scalars. These are just scalars. These are like they are literally constants. If I guess it's been a little bit since we saw what the definitions were, but phi is just this number. It is a number 1 plus the square root of 5 over 2. Phi bar is just 1 minus the square root of 5 over 2. A very good question. So, great. So we proved that equation. Yay! Are we done? Yeah, base case. So what is the base case here? What do we need? Yeah, so we need actually a couple of different base cases because we assumed two things. And so if we're going to ever use this inductive hypothesis, we're going to have proven two things. I hear people saying we need to prove it for 0, 1, 2, or 2 and 3. We can just do it with 0 and 1. And we started out with just this. So we will only need two base cases. Let's look at a formal proof. We prove the result by induction. Suppose that the desired formula holds for n equals k and n equals k minus 1. We prove the formula holds for n equals k plus 1. Now, the way in which we did the working out of the equations we did it backwards. We were like, what could we show that would help us to prove this equation? Now, this is a situation where you can think backwards when you're trying to come up with the proof, but you shouldn't write the proof backwards. You should write the proof forwards and make sure that you are going from things you know to things you would like. So we shouldn't say, if we could show this, then we'd be done. If we could show this, then we'd be done. We can go forwards. We can say, we observe that since phi and phi bar are the solutions to the equation x squared minus x minus 1 equals 0, we have these two equations. Multiplying these equations by phi to the k minus 1 and phi bar to the k minus 1 respectively. So multiplying the first one by phi to the k minus 1 and the second one by phi bar to the k minus 1, we find this. Now, rearranging that, we get this formula, which you will remember was the thing we were trying to show. By our inductive hypothesis, the right-hand side equals fk plus fk minus 1, which equals fk plus 1 by the Fibonacci relation. We conclude that fk plus 1 equals this left-hand side. And now, again, we were talking about base cases. So again, we have two base cases. So what we need to say is just that the first two values, which were 0 and 1, do in fact follow this formula, and it's pretty simple to show. We just need to write out the formula and say 1 over the square root of 5 times, and this is going to be 1 minus 1, so that's clearly 0. And in the second case, it's slightly more complicated. You would probably, if this were a formal proof, just write out what phi and phi bar were here, just to show that this, in fact, does cancel, and you do get 1. But yes. Note that it is actually really important to show the base cases hold here, because if you had different starting values, you would have a different sequence. You could define another sequence that is not the Fibonacci sequence starting at 0, 2, and the base cases would not hold. There would be a different formula, and we'll get to that in a moment. But for the moment, this completes the proof for the Fibonacci numbers. Are there any questions about this? How do you determine how many base cases you need? Great, great question. So here in the inductive hypothesis, we needed 2 because we were going to, in order to get fk plus 1, we knew that we would have to use this relationship between fk and fk minus 1. So we knew we could get fk plus 1 from those two. And so it made sense to make assumptions about what those two were. If there were a recurrence relation which had 3, then we might need 3 base cases. And sometimes you actually need to assume it's true for all of the preceding numbers. So that's called strong induction sometimes, but you don't have to worry about the terms. They're all just different kinds of induction. Just basically, if you are confused about how many base cases you needed, then just write in some values. Say like, okay, well, what if k equals 1? I'm going to prove it for f2, but I'm assuming something for f0 and for f1. So then I need to just have base cases of f0 and f1. And since when I've got f2, I'm going to use f1 and f2 to work at f3. There's no magic here. This is just like simple logic. In general, proof writing should never be about magically applying a formula or a formulaic approach. It's just, induction is just actually how we think about these things. It's just a smooth way of writing it down. So now that we have seen this for the Fibonacci sequence, let's look at the general formulation. I'm not going to go into this in super much detail, but I wanted to at least touch on it. Given a linear recurrence relation, so linear recurrence relation is if you have some initial values for a sequence, and your next value for the sequence is determined by the previous k values of the sequence in this linear equation. Can we express the entire sequence with a closed form equation? So in this particular case, for the Fibonacci sequence, we just had 2 initial conditions, And this was just a very simple linear recurrence, which was just this plus this. And there were only two of them, k equals 2, and the w's were both 1. But you might have another recurrence relation where, you know, the next term in the sequence is the previous term times 3 minus 2 times the term before that plus 5 times the term before that. Can we express it with a closed form equation? Closed form in this case means just that we can write it down without reference to any previous numbers. So for example, to any previous numbers in the sequence. So for example, for the Fibonacci sequence, you can use Binay's formula to calculate the 1000th Fibonacci number without working out any of the previous ones. Whereas the recurrence relation would sort of mean you'd have to do it one by one. So is there a closed form way to avoid doing all that recurrence thing and just go straight to the answer? And the idea behind this is going to be exactly the same as what we just did with Fibonacci numbers. It is not super obvious. I'm just going to say it, but there already was a comment in the chat about this. First of all, like how many terms would you probably want in your induction? How many base cases would you want? Yeah, you'd want k. You want k because in order to prove something about an, you're going to have to make assumptions about the previous k ones. So if you did this with k base cases, you're going to have to show some analog of what we showed before. And what you're going to end up with is if you have you're going to have what's called a characteristic polynomial. This is the characteristic polynomial. I'm sorry, there's a typo. In the posted slides, I will fix that typo. These should all be minuses. It should be x to the k minus w1, x to the k minus 1, minus w2, x to the k minus 2, all the way down to minus wk. That is your characteristic polynomial. And again, in the case of the Fibonacci numbers, these, the characteristic polynomial is just x squared minus x minus 1. And that is because we had just coefficients of 1 and 1 here. Okay. So the characteristic polynomial, x squared minus x minus 1, was just that polynomial that we were looking at phi and phi bar being the roots of. But in general, we can have a more complicated characteristic polynomial that looks like this, only again with minus signs here. Then the overall formula is going to be that a sub n is going to be just some constant times the nth power of the first root plus some constant times the nth power of the second root, and so on. Where the constants are going to depend upon your initial conditions. Now, in the case of the Fibonacci numbers, we had just 2 roots because the characteristic polynomial is a quadratic polynomial. It was x squared, again, minus x minus 1. Now, in general, we're going to have a degree k polynomial. And so it's going to have k different roots. And so we are going to have the general form of just the powers of those solutions to this polynomial equation with coefficients out in front. Now, I realize this is a lot to take in, and you don't have to be understanding this. I just want to give you a sense of why this in general would be true. If you imagine going back to the inductive step that we had before, what we were trying to do is basically plug in this formula into each of these terms. And if you plug in this formula into each of these terms and rearrange everything and separate out the terms associated with the individual roots, you're going to get terms associated with each of these roots. And each of these is going to give you this characteristic polynomial. So you're going to, in doing your inductive step, you're going to have this characteristic polynomial turn up again and again. So just again, before, when we were looking at the Fibonacci numbers, we had this characteristic polynomial, which is the same as this one. And we could multiply it by some things, and we could get exactly the relation that we were trying to show, we were trying to use for induction. Now, this is the same, if you do the algebra, you will see that this is exactly the same approach you will need for any number of terms in your recurrence relation. Now, one question that you might have is why these constants in the front? Why do we have this C1, C2, CK, and so on? Well, it turns out that these are sort of degrees of freedom. We had k degrees of freedom in the initial conditions for picking the sequence, a0 through ak minus 1. And so we're going to have k degrees of freedom in expressing our sequence. If we didn't have these constants, if it were just the sum of the nth powers, then there would be only one sequence. It would be an equals this thing. But we know that there are n different choices for how to start the sequence. And given that there are these n different choices for how to start the sequence, we're going to clearly have to have n different parameters for how to describe every such sequence. What do I mean by degrees of freedom here? Degrees of freedom it's like free parameters. And this is just an intuition. So if you don't get this, it's totally fine. But basically, the idea is that if you changed any one of these initial conditions, you change the entire sequence. And you have these k independent things which you can change. And so you're going to have a formula for the sequence which depends upon k different knobs that you can turn. And you can solve for these k different knobs. How would you work out what these C1 through CK are? In practice, suppose I gave you a linear recurrence relation with some initial conditions. And in response to the question, are they random variables? I wouldn't call them random variables because in any particular circumstance, you would be given them. For example, for the Fibonacci numbers, you're given the initial conditions. First one's 0, second one's 1. Yeah, so somebody's suggesting gradient descent. It's way simpler than that. It's literally just solving a linear system of equations. You just write out the first one, a0 equals c1 times, this one is just going to be 1. a0 is just going to be c1 plus c2 all the way up to ck. a1 is going to be c1 times this thing which you know, because it's the root, one of the roots of this equation, plus c2 times the root of this equation, and so on. And in general, you can just solve a linear system to work out what C1 through CK are. Now, again, this is just a sketch of how you would do this. I wanted to give you a connection to how to solve linear recurrences in closed form. If you didn't really get this, don't worry about this, but just to suffice it to say, the Fibonacci numbers have a closed form. In general, any linear recurrence relation is going to have a closed form, and one of the ways you can prove it very nicely is by exactly the same kind of induction as we used with the Fibonacci numbers. Let's look at a final problem here. Alice and Bob are going to play the subtraction game. There is a pile of n stones. Starting with Alice, they take in turns removing either 1 or 2 stones. The last player to remove a stone wins. Which of them has a winning strategy? This is sometimes called NIM, but it's confusing because there is a game that is more appropriately called NIM. how would we go about trying to work on this problem? Suppose you were given this. What would you do? Like, how would you go about trying to do it? Yeah, probably like small examples. Just play around with it. Let's start with some small cases, maybe n equals 4. Let's try random moves. Alice is going to take 1 from n equals 4, so there are 3 left. Okay? Now let's say Bob takes 1, 2 left. Oh, that's cool. Alice can win. So maybe Bob shouldn't have done that. Maybe Bob should have picked 2 when there were 3 left. Nope. If Bob picked 2 from 3, then there's just 1 stone left, so Alice still wins. Okay. So if n equals 4, then Alice should definitely take 1, because then Bob can't do anything to stop her from winning. Okay, so we know that if n equals 4, Alice has a winning strategy. Cool. What if n equals 5? Let's try that same strategy again. Alice takes 1, then 4 are left. What happens now? Ah, yes. So we knew that if you start with 4, then the starting player wins. And now the positions are reversed. If Alice has taken 1 and there are 4 left for Bob, that means that Bob is now the starting player. So Bob has a winning strategy from 4. So we're not done, right? Because Alice decided to take 1. What if Alice took 2? And then backtrack. And Alice is probably going to take 2. Then there are 3 left. So what happens now? Bit of disagreement, but yeah. So if there are 3 left, we already saw that whatever Bob does, Alice is going to win. If Bob takes 2 from 3, then Alice takes 1. If Bob takes 1, then Alice takes 2. Okay, so that's cool. What do we think? Are there any bad values of n? Like Alice can win for n equals 4, Alice can win for n equals 5. Is anything bad? Any suggestions of bad values of n? Yeah, so if n equals 3, we already knew that n equals 3 is bad for the player who gets landed with it. Previously, it was Bob who was getting landed with n equals 3, but now if Alice starts out with 3, then if she takes 2 away, then there's 1 and Bob can just take that. If she takes 1 away, then there are 2 left and Bob can just take that. So nothing she does works for n equals 3. And there's also a suggestion that for n equals 6. And the reason is there that whatever she does is if she takes 1 away, there's 5. If she takes 2 away, there's 4. And that means that Bob has a winning strategy. So for n equals 3 and for n equals 6, Alice is not going to win. But if n equals 4 and 5, then Alice is going to win. Do we have any thoughts on what the pattern is? And seeing some suggestions? Certainly does look like multiples of 3. N equals 3, n equals 6. Great. Maybe multiples of 3 are bad for Alice. Let's see if we can prove this. So, I'm going to, and really good question from Melissa. Yes, 3 is very much related to the number of stones we were allowed to take. We will get to that in a bit. So let's just go through a formal proof, but sort of working it out as we go. We will prove by induction that the starting player wins unless n is a multiple of 3. So suppose towards induction, before I go through that, what do we think we will need as, like, how many inductive hypotheses will we need? How many things will we need to make assumptions about? This is like the same as the number of base cases we need. How many base cases? So there's a lot of suggestion of 3 base cases. I actually think we don't need 3 base cases. We can do it in 2. It's not, you know, it doesn't matter if you take more assumptions than you need. You can prove 3 base cases. But I think we're actually only going to need 2, and we'll see why. So suppose towards induction, the statement is true for n equals k and n equals k minus 1, then we'll prove the statement for n equals k plus 1. Okay, so that's an induction where we are taking 2 base cases. And so we can divide into some cases here. What are some good cases to divide into? Remembering that we're trying to prove that the starting player wins unless n is a multiple of 3. Yeah, so there's some suggestion of whether n is a multiple of 3 or not. Okay, yeah. So you could do that. I'm going to break into like a little bit more. I'm going to break into exactly what the remainder is when you divide by 3. So whether it's a multiple of 3, whether it's 1 more than a multiple of 3, or 2 more than a multiple of 3. So there's 3 cases for what it could be. Well, in the first case, k plus 1 is a multiple of 3. So what happens here? We want to show that n is, since n is, in this case, k plus 1, a multiple of 3, that the starting player does not win. So what we need to show here is that no matter what the starting player does, they are going to lose. So we can try both possible things. Alice removes 1 stone, then Bob gets a pile of k stones. But we have our inductive hypothesis. We know that if k is not a multiple of 3, then it's a winning position for the first player. So Bob has a winning position if k is not a multiple of 3, and if k plus 1 is a multiple of 3, then k is not a multiple of 3. So that means that Bob has a winning strategy by our inductive hypothesis. But what if Alice removes 2 stones? In that case, Bob gets a pile of k minus 1 stones, and that's also a winning position, because if k plus 1 is a multiple of 3, then k minus 1 can't be a multiple of 3. So by our inductive hypothesis on k minus 1, then that's a winning position. So in both of the possible situations which Alice can do, Alice is going to lose. Now, let's, the reason I divided into 3 cases, you can see now if k is a multiple of 3. So if k plus 1 was 1 more than a multiple of 3. Now in this case, we want to show that Alice has a winning strategy, because n is k plus 1 is not a multiple of 3. So we need to come up with a winning strategy for Alice. In this case, Alice can just remove 1 stone from the pile of k plus 1 and get a multiple of 3. Now Bob gets a pile of k stones, and by the inductive hypothesis, we know that a pile that's divisible by 3 is a losing position. And that means that Alice is going to win. Alice has a winning strategy, just take 1 away. And similarly, if k minus 1 is a multiple of 3, then what's the winning strategy here? We start out with a pile of k plus 1 stones. What's the winning strategy for Alice from a pile of k plus 1 stones? Yeah, just take 2 from the pile. You can take 2 from the pile of k plus 1 and get a pile of k minus 1. And this is now a pile that's divisible by 3, which by our inductive hypothesis is a losing position. Therefore, Alice is going to win here too. So we can see that it sort of repeats. Every 3, you get a losing position. And in general, 2/3 of the time, Alice is going to win. Therefore, from our casework, we confirm that k plus 1 is a winning position for Alice if and only if it is not a multiple of 3. Now, what else do we need here? What do we need to do to complete our proof? Base cases, yes. How many base cases do we need? So if we were making our inductive hypothesis with assuming 3 things, then we would need 3 base cases. In this case, we only assumed 2. We only assumed the result was true for k minus 1 and for k. So we're actually only going to need 2. So the base cases, we can just take the 2 smallest values again. That's just going to be n equals 1 and n equals 2. So neither is divisible by 3. So we want to show, since they're not divisible by 3, we want to show they're both winning positions, and they're trivially winning positions. If you have just 1 stone, then Alice takes it. If you have 2 stones, then Alice can take that too. Okay? Are there any questions about this? There was a suggestion raised that the number 3 was related to the number of stones that we can take. And I'll let you work out for yourself that if we can take 1, 2, or 3 stones, then the result is going to work. But instead of being divisible by 3, it is divisible by 4. If you can take 1, 2, 3, or 4 stones, then the winning positions are everything that's not divisible by 5. And a similar proof will hold for that. This is connected to a whole lot of different what are called combinatorial games. And there's an entire field built up basically from analyzing the connections of other games to this particular game, the subtraction game. This is fundamentally important in game theoretical analysis. But it all basically comes down to this simple kind of induction argument. I'll let you delve into that a little bit more. You might have also seen a version where the player to take the last stone loses. That's called the Misère version, which is sometimes actually more common. There is a similar solution for that. It's not exactly the same. And the same induction kind of argument will hold. Now, before we finish, I just wanted to show you a final cool fact. You might be tempted in situations like this to prove a result by induction. But sometimes when you're asked to prove a cool summation formula by induction, then you can actually do it using what's called telescoping sums. And I just wanted to show you this because it's the most beautiful thing. If you rewrite this right-hand side, you can express each of the terms as the difference of 2 things. Here, 1 over 2 times 1 is just 1 over 1 minus 1 over 2. 1 over 3 times 2 is just 1 over 2 minus 1 over 3, so on. And they telescope, which is to say that the 1 over 2 cancels, the third cancels, all the way up to 1 over n minus 1. All of these cancel, and you end up with just the first term and the last term. This is basically an induction proof in one line. You don't have to say that this is, you don't have to say that this is by induction because you just did it in one line. There's no induction involved. But it is essentially the same idea as induction, just much slicker. Okay, I will stick around for a couple minutes to answer any additional questions that exist. And next time we will be discussing contradiction, and that will be on Friday. I also remind you that Vincent's office hours are going to be tomorrow morning at 10:30 Montreal time, and we'll post by Slack and email about what the Zoom link is for those office hours. I'll remind you again to take a look at the problem set. Look at it early. Thanks for coming, everyone.